Hello. Hi guys, good morning. Welcome back to a new video. In this becomes problem number 4 of contest 387 of today's weekly contest, which we bring in every week for bi-weekly and weekly after the contest. Cool. In this we are going to see distribute elements into two arrays too. Now please don't go on to other solutions because of Leetcode weak test cases, n squared solution also got passed, and this should not have been passed for this problem. Many people have got there, and that's the reason the number of submissions are quite large, because people don't even know that their solution which they have written is O of n square and not O of n or O of n log n. But we will understand this, how this can be done. I'll show you a very great trick. Again, that's a trick, just an optimization on top of our standard data structure, which is Fenwick tree and segment tree. Let's see of what this says. Although this problem is actually of Fenwick tree, but we will see it and we will learn a data structure which will help you a lot in your CP journey. Cool. Let's study. It says that again, it has a version 1 also, which is very easy, which we might not end up bringing because it's a very easy problem. But yeah, let's see this problem. It says that you are given a one indexed array of integer nums of length n. Okay, which means okay, the array is one indexed and I have an integer array called as nums. Now I define a function greater count. Now what is that function? It says that greater count, I have given this array ARR and this is the value, which is this specific value is the value, and I have to return the number of elements in ARR that are strictly greater than value. Now, as soon as you must have heard this, you must have thought, Aryan, that is so simple. I'll simply sort this array. I'll simply sort my array ARR 1, 2, 5, 9, 11. And I want to know, okay, value, let's say this is my ARR. And I'll know, okay, my value is, let's say 12, or let's say my value is 8. Let's say my value is 6. Then I will simply do a binary search, and then I would know that greater than 6 I have 2 elements. So bro, for sure the answer will be 2. So bro, it is very simple. I will simply use a binary search and will simply find my greater element in log n time. Aryan, so simple question, bro. Let's read the question, then we will go on to it. Cool. Now, the next says that you need to distribute all the elements of nums, because your nums is the input. You need to distribute all its elements into two arrays, ARR1 and ARR2. Now, using AND operations, which means on every element, I'll apply one operation and will choose and will try to decide if I should put this element in ARR1 or ARR2. Okay, great. Now, in the first operation, please append, again, in the very first operation, please append nums of 1. Again, remember, the array is one indexed. So nums of 1 is the first element itself. So append nums of 1 to ARR1. And in the second operation, append nums of 2 to ARR2. So in the very beginning, whatsoever I had a first and the second element, okay, first element, again, let's imagine this as ARR1, this as the ARR of 2. So first will go to ARR1, second will go to ARR of 2. Now from the third element, the things will start to get clumsy. How? That afterwards, okay, after the first and second element have gone, now from the third element onwards, things will start change, and I have to apply this operation. Operation is that greater count of ARR of 1 of nums of I, which means I have to go and search nums of I in ARR of 1, which is an array, and then if that count, and remember what is the count? Count is saying that if I search for a value which is, in case this nums of I, in the specific ARR, then number of values greater than this specific value which I am trying to search, which is nums of I in this case. Which means that, okay, your ARR1 is this, then you have to go and do this kind of binary search on ARR1 and then on ARR2, okay, and whosoever is larger, as you can see, whosoever is larger, I will append nums of I in that. So you can see if ARR1 greater count value is larger, then I'll append my nums of I in ARR1. If ARR2 is larger, then I'll append nums of I in ARR2. And if both are same, then I will say whoever has a smaller size, by default who has a smaller size, I'll append in that. Okay, that seems easy. No, I know, okay, I have ARR1. I'll simply go and apply binary search in this. I know it is my ARR, so I'll go and simply apply my binary search on this ARR1. And I'll simply go and apply binary search on this ARR2. And then I can simply know what is the greater count. Simple. Bro, okay, if you had known, great. That's a login operation. But bro, then you have to append your nums of I in the that specific ARR. So when you have found the location, okay, there's 6. Now you have to append that 6 into its location. So this 6 will come here. Now in an array, again, you know that you can only apply binary search on an array. You cannot apply binary search on a multi-set or a priority queue or like these. You cannot do that. You can only apply on your vectors or arrays. So in that, as soon as you have applied, your next operation is okay, applied, great, whosoever is greater. Now in that specific array, either it can be AR1 or AR2, you have to insert this element. Now 6 needs to be inserted. Now I'm not saying insert anywhere. I cannot insert in the end, because inserting in the end takes off one time, but I'm saying insert at the correct location. Why are you insert at the correct location? Because next time also you will have to apply binary search on the same array. So to apply binary search, you have to insert at the correct location. And inserting in the correct location in a vector will take O of n time, because that insertion, you have to shift all the elements to the right. Actually, a vector, how it works is you will insert something, that everything will shift to the right. So that one insertion will, in worst case, will take O of n time. That what we cannot afford, because I have to apply n operations. On every operation, I will do a binary search which will take log n time. I have to apply n operations. In every operation, binary search will take log n time. But after applying binary search, insertion of that binary searched element in the vector back will take O of n time. So it will be actually O of n square in worst case. And I can very easily see O of n square will not work. Maximum I can do is O of n log n. That's it. Or maybe like roughly equal to that, O of n log n or O of n log n into log n, like this. But I cannot do O of n square for sure. Bro, so this, again, you will see that this approach will still pass. And for sure, later on in future, it will not pass, because it is obviously wrong. In this case, what we have to do is, again, if you had remembered searching of some specific element more than, less than, if you had remembered something like that we had discussed in this video. In this video, when I taught you Fenwick trees, I taught you a problem in which, if you had remembered, in which you are given and you have to find the number of elements greater than a specific element, number of elements less than a specific element, which means, okay, some things are in a sorted form and you can work on the Fenwick tree on that part. So one intuition, again, for that you should be knowing how a Fenwick tree works, and you should have watched this video to get the entire intuition of how a Fenwick tree works. But considering you have not watched it, it's your loss though. Considering what if you have not watched it, but still, let's say if you still want to figure out, Aryan, now the only issue I got is that I have to do a binary search on. I have to do a binary search, means lower bound, upper bound, like this kind of search I have to do on a vector. And the issue with, okay, multi-set, I can, if I had a multi-set, okay, let's say if I had a set, Aryan, if I had a set, then the best part is, for a set, I can do insertion in log n time. I can do insertion in log n time. I can do deletion of an element in log n time. I cannot do a binary search on my set. I cannot do that. Why? For a vector, I can do an insertion. Again, when I say insertion, I mean insertion at the correct place. That will take O of n time. Deletion again will take O of n time, and binary search will take O of log n time. Right? Now this. Now I want both things. I want insertion in log n. Again, for me, deletion is no more there, so I can just erase this. I want insertion in log n time. I want binary search also in log n time. So is there anything I can mix them up? Again, for mixing up, the root algorithm for that which we can use is Fenwick tree, and for sure segment tree is the father of Fenwick tree. So whenever I say a Fenwick tree, I actually mean by saying that anything you can implement by using a Fenwick tree, you can for sure implement by using a segment tree. But we don't choose to do a segment tree because its code is pretty large and it's not easily writable in a contest nor in an interview. So that's the reason I always focus on either a Fenwick tree or an alternative of a segment tree. I will not touch on segment tree until it's highly required, because segment tree code is not feasible for an interview. Now, coming on back. we know that we want a mixture of this. Now, for the folks who have been doing CP or who have been following us for a long time, because this problem has come after a long time, who have been following us for a long time, they must have known this can be solved by policy-based data structure. So that data structure is a mixture. What has been built, like I'll show you, there's a very good blog on Codeforces about policy-based data structure. So you can just go and search this blogs by admins. Just write admin policy-based data structure blog. Now in this blog, you will simply see that like you had a tree-based data structure. Now it is just comparable to your simple segment tree and your Fenwick tree, and you can see here is your ordered statistics tree, which is the our ordered tree, and you can also say it as a PBDS, policy based data structure. It is kind of an index set, which we can say, and this is how it works. So what it is simply, you have to simply do some imports. Now this is, I'll show you every stuff, but you have to simply do some imports. Then it is an ordered set. I will show you. It's just simply as you define a multi-set or a set, it's same like that. In that you can insert some elements as you do in a set, insert the elements. In this, the best part is find by order and order of key. This is the operation which will help you do and replicate your binary search kind of a concept on a set, right? So let's take this again. This entire content you will not find in this specific blog, but yeah, this is the very detailed blog if you want to understand how everything from root, and also it has multiple questions also which you can try. As you can see, problem 128, 190, 151, like 1521 and 1439. So you can try all these problems right now. If I come back and show you that how you can actually use this policy, again the root thing you have realized is that you want to use a policy based data structure in situations when you have to do insertions, you have to use the facility of an ordered set, and you also have to find the location or the index of that element, or maybe find that, okay, what is the order of that element. I'll show you. I'll first show you that what are its two capabilities, and whenever you want to use any of these two capabilities, and whenever you feel like no, that okay, I have to use vectors and I have to use the capability of vectors and set together, then you can use your PBDS. Now, firstly, you have to do one thing, a simple import. Again, the explanation of the entire import and library, you can just look for here itself. You can look for the entire thing in here itself. The entire library, you can find it here. Now, and if we come on back, then you will simply see that you have to import this also. Again, this is entirely, again, the entire explanation of this is written here itself. No way whatsoever is from my mind. Now, this is the type def which you have to define for your int as a ordered set. Again, you might say, Aryan, I have to remember this. You can, but I'll not recommend it, because in an interviewer will not ask this question very rarely. It's mostly for the programming, competitive programming field. Now, you will have int. This is the exact same thing if I write, okay, if again, remember, it's a set. Again, remember, it's a set. So it will have only unique values. Remember that fact, which people keep on forgetting. It is a set, it will keep only unique values. So as I write a set of int of s, same way this int reflects this specific int. Now let's imagine if you have to write, in worst case, a set of pair of int comma int. Then in this specific type def, you will just modify one thing. Instead of this int, put a pair of int comma int. Put a pair of int comma int. That's it. So now this is your index set, is your s which you have defined, right? Okay, now this you will use, your index set you will use here. Index set, the same way you have defined your this specific set, now it's your index set. You can name this as any variable. Now that is s. Now you can do simply one thing, insert some values. So in your data structure, you have inserted the values 2, 3, 7 and 9. Again, they're inserted in a sorted order. They are just using the facility of a set itself. Remember, it's a set, not a multi-set. Now, when I mean a set, I mean it will show the unique values only. If I write a 9 again, it will be just 1 9. Now, if I ask you, there are two basic operations. First is find by order, which will say, okay, element 2. Find the element in the index 2, and indexing is 0 based. So when I say find by, find at the index 2, what is the value? Find at the index 2, what is the value? So I will go and check, okay, at the index 2, if I just put the indexing. Again, Aryan, it's a set. How is indexing possible? I'm saying it's a mixture of set and vector, because if you had remembered our Fenwick tree, we actually make a vector itself, and then on that vector we can actually apply this operation. So that's his parent is how a Fenwick tree or a segment tree works, because it's also a tree based data structure. Now if I do a indexing, so you will see at the index 2 I can simply say, bro, the value is 7. So find by order, again, that's a pointer. If you have to remember, it's a pointer to the index 2 that will point to the value 7. So I can easily say the value is auto fx is the iterator at that specific location, which is at the index 2. I'm pointing at the index 2, and then I can get the actual value by simply readdressing that and say, okay, value at that iterator, give me that value. So star of that it or star of that x will give me the value, which is 7. So this is first operation. Second, most important, again, the first operation you saw that if you want to find the value at some specific index, you can simply go and find that value in a set by using a PBDS. Second operation, which is most commonly used, is that order of key, which says give me the position of a 7 in a set. Again, remember, it's sorted. It is ordered. It is sorted. So give me the position of a 7 in this set. So it will go and get this position of 7. Position of 7 right now is 2. So he will give you, y will give you a 2. Will give you a position of 7. Aryan, what if my element is not there? Which means if I ask for a position of 6, he will still go and give me a 2. Next higher, it is giving you a next higher. So it is replicating your lower bound behavior. This is replicating your lower bound behavior, and that too on a vector like array, right? Vector like data structure. So these are the two main and the most important things which you have to know about a PBDS. So what, let's say if I ask you, okay, Aryan, if I go and find order of key of 8, like my key is 8, and if I want to find its order of key, then it will go and give me the index 3. So this I will actually use to find out. Aryan, how you will use it? Simply, bro, I know one thing. I know I have to search for some element. Let's say I have to search for 6. And again, when I say search, I mean the number of elements more than 6. It was saying more than 6. So it was not saying equal. If you remembered, you have to return more than, whereas here strictly greater than the value. More than value I have to return. So I will simply say, bro, my basic task is, yeah, I have to go and return the value greater than 6. But it's a PBDS. There is no concept of upper bound. There's only concept of lower bound. As we saw that there's a concept of only lower bound. There's no concept of upper bound here. So what I can do, I want the value greater than 6. So I can by default increase the value to next value, which is 7. So for sure, I will go and search for a value 7 now in this array. Let's say if I would be finding, if I want to search, do a binary search for a location, for a value 5. So I will increase it to a next value, which is 6, and then go and do a order by order of key of this value, which is 6. And this will say, okay, bro, it will give me an index of 2. I know index of 2, which means all the elements after index 2 are more than what? More than 6. And I want the same value, which is greater. If you remembered, I want the same value, which is greater count. So, and how to know how many elements are actually greater? Simple. You know the entire size of your multi-set, which is this specific size, which is n. Let's say n is 4. This index, it gave you -2. This index, it gave you 2. So elements which are more than are actually 2. So this is the number of elements which are more than my element 5. And that's how you can actually use your PBDS. Cool. Now, Aryan, what's time complexity? Same again. The same way. It's log n. It's log n for you. Now, every operation which you do, insert something, check for something, everything. This inserting, log n. This checking, log n. So if you want to find the index, find by order, log n. If you want to find the actual, the location, lower bound thing of a specific value, again, log n. So that's how you can take the advantage of both set and your vector, and then use it. And again, you have to write some boilerplate code, which is this specific piece of code which you have to write, which means this line extra you have to write, this line extra, sorry, this line extra, and this line extra. 3 lines you have to write extra, and after these 3 lines you can simply start using your index whatsoever you define. Here if you define a PBDS, use by that name, or you can define by any name which is not used, which means you should not write a simple set, because we already have a set data structure. Cool. Now with this, you know that you will use this. Again, there's a way to by scratch implement this by using a Faang victory, but I'm not teaching that because I want to teach this in this video. Cool. Now make sure you remember this fact, and we'll use in future for sure. So how we will use it? Again, as simple as that. We will use exactly what, again, this problem was very straightforward. The only thing was choosing a strategic data structure for it. People pass it by using a O of n square, which should not have worked. That's unfair, but still, no worries. We are with you. So how we'll code it? As simple as that. Firstly, we added a few headers, which we saw. We have to write these 3 lines. So I wrote these 3 lines. Now I use exactly same ordered set. Again, if you remember, I have to take 2 ordered set. Let's take this specific example itself. If I take this example, 5, 14, 3, 1, 2. 5, 14, 3, 1 and 2. Now in the very beginning, ARR1, again, if you remember, ARR1 is a vector, which I will take. ARR1 is a vector. ARR2 is also a vector. And my S1 is a set, S2 is a set. Again, that's a ordered set for you. So in the very beginning, 5 will be inserted in AR1, 4 will be inserted in AR2, and this specific has a set, value of 5, and this has a value of 14. Great. Now comes the next value, 3. Again, for imagining, let's imagine this S1 also as a sorted array. This is a sorted array. This S2 is also a sorted array. But remember, this is not an ordinary array. This is our PBDS. So insertion, all that stuff will be O of log n. Now comes the 3. I will go and have to find how many elements are more than my value 3. So I will go and find it. That's right. I'll go and find it. When I say find it, I will say, okay, I want more than, which means I want more than 3. So I want 4 or equal to 4, like 4 or more than 4. But my PBDS only supports lower bound, which means it will say it cannot give me a more than 3. It will give me a 3 or more than 3. So I have to increase it manually. So I'll increase it manually to a 4 and then go and search for a value 4. Okay, this 4 will land me onto a value which is this specific. Again, the indexing is 0, 1 and so on and so forth. So this will land onto me an index as 0. I know so far this AR1 has one element. AR1 has one element. It pointed me to an index of 0. So how many elements are more than or equal to 4? It has just n, which is one element, minus index, which is 0. So I have one element which is more than or equal to my 4. Okay, I have one element. So greater count became a 1 for this case. I'll go and do the exact same stuff. Increase it, make it a 4, binary search for it, do a order by key, do a order of key. I forgot order by and all, but yeah, you can just simply keep it as it is, as a screenshot, as I have taken it. So you will simply go and find 4. Again, it's indexing 0, 1, 2, 3, 4 and so forth. It will still point it and say, okay, I have one element which is n equal to 1, indexing pointed to 0, so I have 1. So you will see the greater count is again a 1. Now if you had gone back to your main example, if the greater count is equal, go and check whichever has a lesser number of elements, and I will go and check, okay, AI1 has one element, it has also one element. Oh, both are equal. If both are equal, then the problem says that insert wherever I have insert. Okay, if there's a tie, insert in nums1. If there's a tie, insert in nums1. So I'll simply insert this upcoming element 3 in nums1. Okay, I'll insert 3 in nums1. Now 3 is inserted here, 3 is inserted here. Now 3 inserted here in the array AR1, but you know that your S1 is sorted, so it will become a 3 and a 5. Right. One thing you must have thought of so far is it was a set. If I would have used a 5 here in this place, and if I would have inserted a 5 here, so it would have just remained a 5. It would not have become a 5, 5. So I have to modify something so that it should distinguish between 2 5s, right? It should distinguish between 2 5s. I have to do something. What shall I do? Simply, you know that your standard PBDS, what you have taken is a int, which is taking 5. You have to distinguish between two incoming 5s. So add a next factor, which is their index, because index for all of them is unique. So rather than taking an int, I will take a pair of int comma int, because I know that I have to keep all the elements. For me, 5 at index 0 and 5 at index 1, 2, both are different, and both needs to be in my vector, both needs to be in my answer, both needs to give and contribute to my S1. So I will need to put them such that both of them can come in. So I will put an index associated with those specific values. So now I will say, rather than int, I will take a pair of int comma int. And in this pair, first value, again, this pair works the exact same way as normal vector works. The first value will be nothing but my element itself, and next will be its index. Now, Aryan, what all things which you told, that if I am like, for now, like what you are saying right now is, for this, the ordered set will actually become like 2, 0, 3, 1, 7, 7, 2, and 9, 3. Now, if I go and have to search some values, I have to go and search for 6. Because if you remember, I was saying, okay, value 5, find the index with the greater index. Okay, find the index which has value greater than 5. So I will say, okay, greater than doesn't work. Lower bound is the only thing which works. So I'll increase it to 6. But I have to go and now search for what? A pair. So I will have to go and search for a pair, which is 6, something. So what is that something which I should search for? My only task was to search for 6, something. 6, my although indexing I have put just so that I can distinguish between two same values, but index for me doesn't matter as such. If I put a large value, let's say if I put a large value, which means 10, still if I go and do a binary search, firstly it will compare the first value, 6 and 7. 6 is less, so for sure it will go and point here itself. So it will say, okay bro, your index, I'll give you an index of 2, but right now you are safe because here the value was 6. What if I'd ask you if the value would have been 7 here? Which means I would have asked you, bro, go and find the value greater than 6. So you would have increased it and made it as a 7. And for you, if I ask you, by default, you would have pointed here itself. If this would not have been there, you would have pointed here itself, and that would have been your correct answer, because number 7 is more than your 6, so it's correct. So these should be the values. Two values are more than my 6. But if you had put an index higher than the current index, so it will go and compare the first values, it is same, then it will go and compare the next values. This is more, so it will say, bro, I'll compare with the next one. Okay, he will compare this. Oh, he's less. Now he will point to here, so he will say that only values greater than me are this value 1, this only one value greater. That's an issue for you. So you have to put a very less value here, because see, this value, it doesn't matter for you. That was just to search, because now I have to search in a pair. So you have to just put something. You cannot put something very high. You should put something very low. You can put -infinity also here, but I can also put a 0, because I know I will not be searching for these values in my array. So I can put a 0 also here. That will not matter for me. But yeah, safe side, put a -infinity, and that will perfectly work. So now you know one thing, that what value you have to search for. So coming on back to our example, we know that, okay, in this case we had a 3,8, but sorry, 3,5, but we know that what value we'll be searching for a pair. Pair will be value itself plus 1, and then next thing is -infinity or 0. As minimum as possible value. Now comes the next. Okay, put it as 3. Now comes next 1. Search for 1, more than 1, increase it to 2, and then search for 2. Search for 2. Okay, I have 2 elements which are greater, so I have 2 elements which are greater. If I search for this 2, I have just 1 element which is greater. For sure, this is more. Whosoever is more, insert that element in that location. So I will insert 1 here. Now if I insert 1 in this, it will be in a sorted location, so it will become a 1, 3, and 5. Next comes, I will search for a 2. Now if I search for a 2, bro, simply increase it, search for a 3. Now search again. When I say search for 3, I mean search for a 3, 0. Search for a 3, 0. Now let's say if I search for a 3, I'll search and put it here. Okay, because I'm saying more than equal to, so it will give me two values. Okay, if I go and search for a 3, it will give me one value. Okay, no worries. Then okay, this is more, so I will insert my element, which is 2, in my array 1. Okay, I insert that to my array 1, I insert that to my 2, I'll insert that to my 2, and that's how, this is my array 1, this is my array 2. Simply merge them or simply concatenate them. So answer will be 5, 3, 1, 2 and 14, and that's your answer, 5, 3, 1, 2 and 14. That's how you can simply solve it in O of log n time. O of n log n time, because you have to iterate on all the elements, and for every element you have to go and iterate on and see what it's actually PBDS, or what's its actually index. Now code is pretty simple. As you have remembered, I showed you I have to take a pair. So instead of int, I have modified. Again, wherever you have int, put a pair of int. And this is the interesting part. You can replace it with any data structure. You can also make it as a vector of int. You can also make it as a set of int also. That's interesting, right? Cool. Now I will simply have answer as the final answer, AR1 as a AR1, AR2 as a AR2, S1 is a corresponding ordered set of AR1, S2 is a corresponding ordered set of AR2. Now, as you saw that first element I will push back in AR1 and S1 also. I simply, if I am pushing in AR1, I'll also push in S1 also. S1 is to search for binary search. AR1 is to actually put in the answer, and simply in the last concatenate those answers. AR2 simply push back nums of 1, and S2 I'll simply push back. Again, if you can see, I'm pushing in the pair. I'm pushing in the pair itself. I'm pushing in the pair itself. Again, for my simplicity, I would have pushed that as infinity, but while pushing the element in my S1, I have to make sure that I am pushing in. While pushing the element in S1, I have to make sure that I'm pushing in distinct values. So index is actually distinct for all of my nums values. That's the reason I have to put in index, so as I can distinguish between same values. So it's the reason I'm pushing in with the index. Now I will start off with the index 2 and will simply keep on going. I have to search for nums of I, but I knew my order set, it actually works on lower bound concept, which means equal to, but in my problem I have to find for more than. So I do a simple +1, and then I will go and simply do an order of key of this specific value with the minimum value, which is 0. Again, I'll say put a -infinity here, but still it will work. Now order of key, simple, same value, and then I will get ID1 and ID2. These are the indexes in your ordered set. But remember, you have to find greater count. Greater count is number of elements actually greater than your this specific value val in your S1 and S2. So simply find the size 1 and size 2 of your AR1 and AR2, which is the size 1 is the number of elements greater than value in S1, and size 2 is number of values greater than value in S2, in your S2, right? In your S2. Yeah. Now when you have size 1 and size 2, now comes that this is the GC1, this is the GC2. Same what the problem is saying. If my GC1 is more than my GC2, simply push that element in your AR1, and when I say push the element, please push the corresponding pair also in your S1. If my GC2 is more than my GC1, simply push that in my AR2. If both are same, then see whosoever has a smaller size. If both are same, if my AR1 size is small, then push in AR1, else push in AR2. And that's how, just by this specific case, you can simply solve it. And ultimately, you can simply concatenate both AR1 and AR2 in your final answer. This is your answer itself, and that's how you can simply solve it. Now, the time for this is O of n log n. Again, there are multiple log m factors also which will come in, but yeah, roughly it will O of n log n. Space for this is O of n itself, because you will have this internally will take a O of n space for you. Again, that's a slight more slow than your fen victory or a segment tree, but yeah, that's workable. As in, like, it will have a log m factor also in its picture, but yeah, roughly it will be more or less equal to your fen victory or segment tree. And that's how, without even stressing your mind on this complex data structure, you can simply solve it. The only fact I told you this because you should be knowing this if you are doing CP. If you are not, then it's completely fine. There's a high chance your interviewer might even not know this, but you can just tell him it's actually a replication of a Fen victory, like how a Fen victory works. It's actually used that concept and then made on top of it. Cool. Thank you for watching. Goodbye. Take care. Bye bye. I hope that you guys got it. Bye bye. Take care. See you. Goodbye.